All right, welcome to our Unit 3 energy review. Our Unit 3 review with energy. We have heating cooling curves we're going to talk about. Label the 5 regions of both heating and cooling curves, knowing what phases and matter are present in each region and which type of energy, ETH or EI, is being affected. So we're going to have 5 different regions in both, and both of them are going to have temperature on the left on the y-axis, time on the x-axis, again temperature in degrees Celsius or Kelvin on the left, and then time on the x-axis. And we're going to have 5 sections. We're going to start with a slope, end up flat, then another slope, end up flat, and then another last slope. Same thing here with the cooling curve, except we're going down. We start with a slope, then flatten out, slope, flatten out, and then slope. Now, a few important points. On the heating curve, we're going to have our boiling point and our melting point, our TB and our TM. Boiling point and condensation point are the same temperature, but in the cooling curve, it's condensation or condensing. On the heating curve, it's boiling because we're heating it up versus cooling it off. Same thing, melting point and freezing point are the same temperature. It depends on what we're dealing with. So on a heating curve, we have our boiling temperature and our melting temperature. On the cooling curve, we have our condensation temperature and our freezing temperature. And those are going to coincide with those flat spaces on the curve of our line. So looking at the heating curve first, we have our solid phase, and that is where our temperature is changing, our thermal energy is changing here when we have any kind of change vertically on the graph. So we have thermal energy changing here, and then it gets to a point where everything is starting to change from a solid to a liquid, and that's where our activation energy, or interaction energy, sorry, is changing. Our temperature isn't, but there's still energy going in, and that's going into the specific particles of whatever we have that we're heating up. And that's where we're changing from a solid to a liquid. We have a mix of those. And then we get here. Once everything has become a liquid and melted, that's what this phase is here. And we have ETH, our thermal energy, where our temperature is changing again. We get to a point where we get no change in thermal energy, no change in temperature. And that's going to be our interaction energy again changing. No, this time it's a liquid to a gas. We have a liquid gas mix here, and then eventually we get everything turned into a gas, and that's where our temperature is going to keep changing and rising as long as we keep putting heat into it after that, and that's going to be thermal energy there. And it's going to follow the same pattern of the cooling curve, but mirrored. So ETH, EI, ETH, EI, ETH. Here we have ETH, EI, ETH, EI, ETH. And then instead of solid liquid mix, liquid gas mix, gas, we have gas, we have the reverse, the mirror. So we start with a gas, end up with a gas liquid mix, liquid again in the middle, liquid solid mix, and then solid at the end. And notice every time that we have a slope up or down, we are changing our thermal energy. Anytime we're flat, we're just changing our interaction energy here. So which phase changes are endothermic, where energy goes in? That's going to be our melting and boiling, where we go from a lower energy state to a higher energy state. Opposite is going to be where we have exothermic, where energy is coming out of our system. We're going from a that's freezing and condensation. That's where we have a higher energy state, and we're going down to a lower energy state. Our phase changes, chemical changes or physical changes, and why. They are physical changes. Our chemical formula doesn't change. It's still the same substance except for the fact of how it's organized. When water is boiling, what is inside the bubbles? So again, we're changing the water from a liquid to a gas, and so those bubbles are going to be gas bubbles of water vapor. And so water vapor is what makes the bubbles. We're not breaking it apart. Again, we just said that it's a physical change. So it's a physical change. It's still water, and it's just going to be really hot enough to be a gas in that state. Moving on to our constants, we're going to do some calculations here. constants for water. If we're doing anything with water temperature changing, we're using the specific heat capacity of water, which is 4.18 joules per gram per degree Celsius. Uh, if we're doing anything with ice changing, that's different. We have the specific heat capacity of ice instead of water. Again, water is liquid, so those particles are a little harder to transfer energy between each other versus as a solid where they're organized, and when one vibrates, then its neighbors vibrate a lot more easily. Heat of fusion is going to be anytime we deal with melting or freezing, we're going anything between a solid to a liquid or a liquid to solid. And then heat of vaporization is anytime we're boiling, evaporating, condensing, where we're going from a gas to a liquid or a liquid to a gas. And that's that 2260 joules per gram. So going up here to number 3, we have 9850 joules of heat energy are removed from 175 grams of water. Now, if something's removed, we can treat that as a negative because that's going out of the system. It's losing that. So we have 175 grams of water and we're losing this much heat energy. How much will its temperature change? If it started at 75 degrees, what will the new temperature be? So again, we're first, all of these cases, 4, 5, 3, 4, and 5 are all dealing with water. So we put our temperature labeled on the left side of the graph on the y-axis. On the x-axis, we have t, lowercase t for time. And then we point out our boiling and melting points, or in this case, this first case for number 3, our condensation point and our freezing point of water, which are 0 degrees, or 100 degrees and 0 degrees for water. In this case, we're starting at 75 degrees, which is going to be in this area of the graph, and we're going to lower it by some amount that we'll figure out in a second. We're going to start by using that Q equals MC delta T. Now, we have to figure out what is our change in temperature. So we have to solve this for our change in temperature, or delta T. We have M mass times this, so to get rid of that, we have to do the opposite operation. And so M times T, the opposite is going to be T divided by M. We're going to divide by M, and we're going to divide by C. So we move those to the other side, and we end up with delta T, or a change in temperature, is equal to Q divided by M times C. Again, because whatever we do to one side, we have to do to the other side of the reaction, or of the equation. So if we divide by M here, we divide by M here, we divide by C here, we divide by C here. And that's how we get this delta T equals Q over MC. And then we just plug in our numbers. Negative 950 or 9850 is going to go here on top because, again, we're losing it. We're going to put 175 in for our grams, for our mass, and then our specific heat of water on the previous page is 4.18. So we put that in, we plug it in, we get negative 13.5 degrees Celsius. And then if we're starting at 75 degrees, we just do 75 minus 13.5 gives us 61.5 degrees Celsius. So we're between 75 and 61.5 here is this part of the graph. And then we have a negative change of 13.5 degrees Celsius with our heat overall. Next one, number 4, calculate the mass of water that can be heated from 20 degrees to 85 degrees if 19,500 joules of heat energy is added to it. And we're going from 20 to 85. So again, we have our heating curve here. 20 to 85 is somewhere around this. It's about this area that's shaded in. Not quite exact, but again, we're just being close. We're going to be completely in that liquid phase here, where it's just temperature changing, no activation energy or no interaction energy is changing. And we're going to reuse this Q equals MC delta T, but this time we're solving it for mass. So we're going to divide by C, divide by delta T, and get those on the other side of the equation. So we have M equals Q over C delta T. And then we just plug our stuff in again. We have this many joules of heat added in, so that's positive. So 19,500. Our specific heat capacity of liquid water. Again, we're staying as a liquid because we're between the boiling point and the freezing point. We're between 0 and 100 the whole time, so we're going to use liquid water, 4.18 heat capacity, and then we're going to use 65 for the change because we do 85 minus 20 gives us our delta T, which is 65. We plug that in 65.0. So we're going to end up with 71.8 grams is the mass there. Number 5, we have a 4.50 or 45.0 gram sample of water is at 20 degrees Celsius and heated until it completely boils. How much heat energy is required to heat the water and then completely boil the water? So we have two parts here now. We have a heating part, and we have our boiling point part. So part one with just the heating, Q equals MC delta T. As we can see here, we again start at 20 degrees, heat it up until it boils, and then it boils, it's a gas. So Q equals M, which is our mass of 45.0. C, specific heat of water. We're heating it up as a liquid, so we're going to use the liquid heat capacity of water, which is 4.18. And then it to go from 20 to 100 is 80.0 degrees, and that gives us 15,000 joules. So we have 15,000 joules of energy, or 15 kilojoules, from just heating it up. And then we're going to boil it. And we have 45 grams, and we do that times 2260 joules per 1 gram to change it from a liquid to a gas. And so that gives us 102,000 joules. We add those together, we get 117,000 joules, or 117 kilojoules. And again, we know that we use our heat of vaporization because we're going from a liquid to a gas. Anytime we're using gas, we're going to be using heat of vaporization. And then we have our energy biodiagram, our LOL chart, to represent the situation. Clearly label ETH, EI, the system, and energy flow. State whether the process is endothermic or exothermic and how you know. So here we have ETH and EI, ETH and EI, and this circle is our system. We start room temperature-ish, a little bit below, which is that 20 degrees, because 25 degrees is generally what we consider room temperature, or standard temperature. We'll call that room temperature. 25 degrees is generally what we call it. And then we are ending up hot, boiling. So we end up with 2 bars gained in our thermal energy. We start as a liquid and end as a gas. Again, liquid is 2 bars. Gas is going to be 4 bars for that interaction energy. So we end up with double the amount of energy that we started with. So that means energy has to be coming into our system. And if we know energy is going into our system, that means we have to be endothermic, where the system has more energy going into it than it started with, and we have to have gained energy from our surroundings in some way. Thank you guys very much, and I'll see you guys next time.